Alright guys, so for this video, we will be talking a little bit more about Extrema. And it's kind of an exciting time for me because I am using a new touchpad to try to write on the screen. So it may not be the best, but it's kind of cool. I'm excited about it. So I have like a touchpad that goes in my computer so I can write on that and it shows up on the screen. So if we look, today is 3.1B Extrema, so you can write the date here, okay? And we want to talk about what a critical number is. I think we feel pretty decent about this if you looked at 3.1A. But a critical number is basically if the derivative at that number is 0, and C is for critical number. If the derivative at that number is 0, or if f is not differentiable at C, then C is a critical number. There's two options. Critical number, that's an important thing to know. Okay. We can also call it critical value, and critical number is usually an x value. Critical number is an x value, critical value is an x value. So we could have critical number. We could also have critical value. That's another way to say it. Critical number, critical value. Those are both x's, but you could also have something called a critical point. And if it's a critical point, right, if it's a critical point, then it would be an x and a y, whatever those are, okay? So those are some things to just think about, maybe make a note of: critical value, critical point, critical number. Different ways of saying the same thing in a sense, except for critical point is obviously a point. So you can see here's two critical numbers. There's a critical number here at this C value because here there's a sharp turn and the derivative doesn't exist there. The derivative doesn't exist cannot exist for a lot of different reasons. And here you'll notice that it doesn't exist because there's a horizontal slope. It's flat. Slope is 0. This you can't draw in a slope of 0 because of the way it's drawn. If you zoomed in, it wouldn't really work out. So those are critical numbers. Just wanted to make sure we had the definition of that because I don't know if I talked about that. And here's the deal. Relative extrema only will occur at critical numbers. So if there's a relative max or a relative min, it has to be a critical number. In other words, if you have a relative extrema, it has to either be that the derivative doesn't exist or the derivative is 0. So this is kind of important to know. So could an endpoint of an interval be a relative extrema? No, I would say no. So this is saying it is a critical number if it's a relative minimum or a relative max. So just some definitions here, and let's kind of wrap this section up. So critical numbers don't have to produce a relative max or a min. So let me just show you what I mean by that, just so you can get an idea, okay? And then you'll try this problem. So the NYT is for now you try, by the way. So here's the deal. I want to show you something. Like, let's say we made a quick graph here like this, okay? And we took the graph and it was like going up and it went down like this. Okay. Okay, so now let's talk about where we have critical numbers. So let's see, what can we do here? I think actually we could say there's a critical number here. There's a critical number here, right? Oops, not very close to it. There's a critical number here, critical number here, critical point here, critical point here, right? Now what do you notice is that this is a max, this is a min, local max, local min, local max, local min. This one's undefined, these ones are all 0 slope, this is supposed to be undefined. But here we have a critical number because the slope is 0 here, right? But it's still not a max or a min. So watch out, because a lot of people think, oh, it's a critical number, boom, it's a max or a min. It has to be. Not necessarily true. Okay, so pause the video, try this problem right here, find the extrema on the interval. If you don't know how to do this problem, I would go back to the video 3.1a and go through that example. It will give you all of the steps, or just look at your notes. So 3.1a will tell you how to do this. Sorry, this new touchpad is going to be tricky. So pause the video, give that a shot. All right, so hopefully that went well, and now we're going to start talking about 3.2a. So we might just call this video 3.1b and 3.2a, and we'll see how long we can go. We can't probably get through all of these note handouts, I don't think, but we'll do what we can do. So basically what I want to show you is a couple of things. You have this in front of you. In general, the mean value theorem, and you don't even know what that is, but I want to read this to you, just straight up. The mean value theorem says the following, that the slope of the blank, let's take that away, the slope of the, and here's what you want to write in, secant line. Okay. What is a secant line? Well, I'm going to tell you in English. You can write it out if you want. It's y2 minus y1 over x2 minus x1. It's a regular slope of a normal line that cuts through twice. Okay. If you have the slope of that going through the endpoints of an interval, where the function is, and let's fill this in, continuous and differentiable. You need to have it being continuous and differentiable for this theorem to apply. Then that is going to be equal to the slope of the, boom, tangent line. Okay, perfect. To the function at some point between the endpoints of the interval. Okay, pretty simple. Find the slope between the two endpoints. If the function's continuous and differentiable, then there's some place where you can draw a tangent line totally parallel at the exact same slope. They will match up nice. So let's just visually look at what I'm talking about. Don't make this theorem harder than it needs to be. Here's the deal. Okay, so here's the secant line. Let's do the secant line here. So here's the beginning of it. Okay, oops. Here's the beginning of the secant line. Here's where it ends, okay? And we can kind of see the slope of the secant line. It's here, right? We can see the rise of run of that thing, right? Now, as you're going along your function, which is this guy right here, okay? You're going along the function, you're going along the function, and you notice right here when we draw in a tangent line, when we draw in a tangent line here, we get this line right here. Notice the green line and the red line are parallel to each other. That's all this is saying. If you have a continuous and differentiable function, a polynomial is always going to be continuous and differentiable. If you have a continuous and differentiable function, then there must be some place, I don't know where, but there must be some place in between that interval from here, A, in between this x value right here and this x value right here. There's got to be something in between these two blue lines, these two x values of A and B, where the slope is exactly the same as the slope between those 2 points. So you do normal algebra 1 slope, and then you do calculus slope, and you set them equal. And there should be a point C where they equal out. That's what the mean value theorem says. Not actually that complicated if you think about it in those terms. So, a couple things we want to talk about here. I think you have this in front of you. If you don't, that's okay. So the function has got to be continuous and differentiable. We talked about that, so we know that it has to be continuous and differentiable. That's important. On the interval from A to B, these are both x values, by the way, guys. So this is an x value, and this is an x value. We're just calling them A and B. The secant line passes through those values, so here's the x value with a y value to go with it. So you plug in, obviously, to get the y value. And the b value, which is another x value, with another y value to go with it, so you plug in to get that. There's a point where the tangent line is same. That's basically what that's saying. It's just another restatement, actually. So pretty much, there's got to be an existence of a point if you have continuity and differentiability. No sharp turns, no discontinuities, no asymptotes, etc. Nice function. And it doesn't mean that it's unique. In other words, here's the start of this interval, right? Here's the start of this interval. And here's where this interval ends. So we started here at -2 and we ended at +2. How many times were we able to find a slope that matched? Well, once here and a second time here. You'll notice that if you think about this, I'm going to draw these in as, these are parallel lines. Remember the symbol from geometry class? Parallel lines. So these 3 lines are all parallel. What does parallel mean? It means they're same slope. So take the slope via algebra 1. This blue line is algebra 1, just a regular old line between 2 points, this guy and this guy. Take the algebra 1 slope and set it equal to the derivative, which will finally, right, it will get you these 2 points. These 2 x's will be your answer. Okay, there are how many points? There are 2 points that satisfy the mean value theorem. So write in 2 points that satisfy the mean value theorem, and they're circled right there in blue. So you get the general idea of graphically what this is all about. So now let's see if we can do some algebra to get there. And here's some things. If there's continuity and differentiability, so don't forget about that, always say that first, then it guarantees that there will be a point where the slope is the same, the slope of the tangent line is the same. If either of them is not guaranteed, if there's not continuity and differentiability, then the theorem does not apply. Okay. If either continuity and differentiability not satisfied. If either continuity or differentiability, if it's one or the other that's not satisfied, then the theorem doesn't apply. There could be a point that works, but there's not necessarily a point that works, so we can't use the theorem in that case. Okay. Also, there's a couple things that this kind of means, like graphically, there's kind of a point where there's parallel, right? Parallel is graphically what's happening here. So just kind of be aware that we have parallel lines from algebra 1 and calculus slopes being the same. And also with rate of change, I guess it's kind of saying the instantaneous rate of change, which is the calculus slope, is going to equal the average rate of change, which is the algebra 1 slope. This always throws people off. Algebra 1, 9th grade, or even 8th grade for some of you, all of you even. Cool. So we're in pretty good shape right now. So that's kind of what the mean value theorem is. So now what do we do with it? Here's the formal statement of it, okay? So you can kind of see here what's going on. Well, this is basically saying y2 minus y1 over x2 minus, minus x1. Okay, that's the slope of the secant line. And what are we setting the slope of the secant line equal to? We're setting it equal to the derivative. And instead of x, we're changing that to c. So this is an x value, but we're changing that to c, and then we're finding c. Instead of finding x, we're finding c. So don't be confused by that. I know that's a little bit weird. If you wanted to leave it as f of x and find x, that makes it work. That's fine with me. Sometimes people also write it in this form. Another just aware of this. This doesn't matter. You don't need that. But it's kind of like point slope form in a way. Kind of like y minus the y minus y, and then the slope, and then x minus x. Whatever. Don't worry about that green circle there on the bottom. So here's an example, concrete example. Consider this thing right here. Okay, this is a polynomial. I want to tell you something that's important. Here it is. Oh, do I have it? Oh, yes, there we go. Since f is a polynomial, then f is continuous. That's going to be the case. If you have a polynomial, you can automatically use the theorem because all polynomials are continuous and differentiable. Remember that I said that. That's important. And now we want to find the value that satisfies the theorem. Okay, so in other words, I need to do 2 things. I need to do algebra 1. Okay, so I'm going to do algebra 1 over here. Okay, and let's use some different words for algebra 1. Well, it's also called the secant line, and it's also called the average rate of change. Average rate of change. Okay, so that needs to be done over there. And then over here, I'm going to do some calculus. Calculus. I don't know about this touchpad yet. We'll see. Calculus, which is also called the tangent line slope, right? The tangent line slope. You can write that out if you want. And it's called the instantaneous rate of change. Any of these things are all the same thing. Basically, the calculus way of doing it is going to be a tangent line or instantaneous rate of change. The algebra 1 way is going to be the secant line or the average rate of change. So I'm going to give you one concrete example, and then I'm probably going to end the video. I have two x values. I got my x1, if you'd like to call it that, is -5, and my x2 is going to be 1. So if I take those and I try to find the y's that go with them, I simply just need to plug in, okay? This is not that hard. So if I plug in the x1, which is -5 here, I get -125, and then I get 75. So I think I have -50 for that. Okay, possible that mistakes happen. If I plug in x2, which is equal to 1 here, I'm going to have 1 plus 3, I'm going to have 4. So this is basically what's going on. I need to do the algebra 1 slope of this. So what I'm going to do is I'm going to take y2 and I'm going to subtract y1. So I'm going to have 4 minus -50, so I'm going to have 54, I believe, on the top, over x2 minus x1, that's 1 minus -5, so that's going to be 6. So 54 divided by 6, and I think that's actually 9 is the answer for that. Okay? So I'm going to have to stop the video there because we're a little bit too long. We're going to call the next video, I guess, 3.2a simply, and we'll take it from there. So go to 3.2a.